I will present our work, Randomized-to-Canonical Model Predictive Control for Real-World Visual Robotic Manipulation. First of all, I will explain the Visual Model Predictive Control, which is widely used in robotic control. In the Visual MPC framework, we first give the target state as an image to the Visual MPC. Then the Visual MPC takes observation as an image from the environment. Subsequently, the Visual MPC predicts future images through its visual dynamics model based on the current observation. After that, the Visual MPC optimizes the action of the visual dynamics model for achieving the given target state. This process is repeated several times. Then, based on this optimization, the optimal action is executed in the real environment. This is the Visual MPC framework. But the problem here is that the data collection cost. Specifically, we need to collect a large amount of data consisting of images and actions from real world to train the visual dynamics model. But as many of you know, this data collection process is very high cost, and it is sometimes even unrealistic. Therefore, our research objective is zero-shot sim-to-real transfer of Visual MPC, which means that our model is fully trained on simulation and then transferred to the real world. Then how can we achieve this objective? Our key idea is extraction of task-relevant intrinsic features. That is, learning an encoder that can extract features common to both simulation and real images. But once again, to emphasize the difficulty, we cannot use the real images for doing feature extraction, since our objective is zero-shot sim-to-real transfer. In addition, the task-relevant intrinsic feature is also unclear. Then how can we extract task-relevant intrinsic features without any real-world data and its clear definition? Our idea to implement this is the randomized-to-canonical feature extraction. In this model, randomized images are used for input of network to solve the visual reality gap. Then we newly introduced a decoder. The output of the decoder is canonical images in which each task-relevant object is visually identifiable. By learning this encoder-decoder network, it is possible to extract the task-relevant intrinsic features in an unsupervised manner. So this is the overall model architecture of our visual dynamics model. In this model, the observation images and the dynamics model are connected via the task-relevant intrinsic feature. We call this model KRC model. And this is the graphical model of KRC model. Please note that you don't need to understand the detail about this. And the only important point is that the feature extraction part highlighted by the pink color and the dynamics model part highlighted by the blue color are connected as a unified model architecture. And both of the two parts are jointly run with variational learning scheme. So now our Visual MPC framework becomes as shown in this. Unlike the naive Visual MPC described in the first of this presentation, the image is not used directly for Visual MPC, but rather task-relevant intrinsic features are used to perform Visual MPC. And we call this our framework KRC-MPC. To verify the effectiveness of our method, we conducted real-world experiments by using logarithmic law environment. The task is set to valve rotation at a constant velocity. As an observation, RGB image and joint positions of robot are used. Then the target joint position of robot are used as action. The real-world test domains used for evaluation are following 6 domains as shown below. These have a lot of variations of valve color and background condition. To transfer our proposed Visual MPC, a KRC model was trained by using simulation data in which many visual factors are randomized, including texture, camera position, and lighting condition. This is the experimental result of the first test domain. Here, we show the three types of movies, including overview of the test domain and its observation, and reconstructed canonical image. As you can see, the canonical image is reconstructed precisely by the decoder, indicating that our method can extract task-relevant intrinsic feature from the real image. And thus, robot can rotate the valve at a constant velocity. Then these are the summarized experimental result of the first three test domains. And these are the experimental results of the remaining three test domains. We additionally conducted a comparative experiment with several feature extractors to evaluate the effectiveness of the randomized-to-canonical structure of our method. The compared methods are the following three structures. The first method is the KRC, which is our proposed method. And the second method is KR2, whose input and output of the feature extractor are both randomized images. Then, the final method is KC2, whose input and output of the feature extractor are both canonical images. We evaluated these three methods by their control performance in the 6 test domains described earlier. We can see that our KRC can achieve the better performance than the other two methods. So that's all for my presentation. Thank you so much.